Okay, so last time we were talking about context-free languages and context-free grammars, and grammars in general, but the only examples I actually showed you were context-free grammars. And the one we looked at in detail was this one. And then we did a particular example where we used this grammar to generate a string in the language of the strings generated by this grammar. I'll call this grammar G. And this is looked something like this. Maybe we had a little bit longer one. 0, 1, 0, 1. B. So using this grammar, we generated the string 00 hash 11, and therefore this string 00 hash 11 is contained in the language that's generated by that grammar. Okay, so a context-free grammar, well then I put up a general description of what a grammar consists of. It's this for tuple where this is the set of variables. This is the terminal alphabet. These are the productions, or the rules. This is an example of rules. And then S is the start variable. Okay. And so here, or actually, yes, start variable. So here, A is the start, and we're using this production. A goes to 0, A, 1, and then we're using it again, and then we're using the A goes to B production, and then B goes to the hash production. And in this grammar, you notice that there are choices. We could use this. We could have actually done a derivation that just has A goes to B goes to hash. So this is also in the language that's generated by this grammar. And then we can just sort of look at this and see, well, what really is the language that's generated by this grammar? And it's the set of all strings consisting of some number of zeros, followed by a hash, followed by the same number of ones. So L of G is equal to language W, where W is some number of zeros. Actually, make it n, followed by a hash, followed by 1 to the n, and n is greater than or equal to 0. Okay? So that's the language that this grammar generates. Okay. So when we're thinking about using a grammar in a forward direction, then we're saying the grammar generates a sequence. We'll see in a minute, or so soon, we're going to set up a machine, which is a generalization of a NFA that can take in a string and accept or reject it. So that's more in line with what we did when we were talking about finite state machines. Instead of generating sequences, when we were looking at finite state machines, we were just looking at whether the machine accepted or rejected the string. Okay, this is, by the way, this is called a parse tree. And oftentimes, you do have not just the accept and reject question. If you have a string already, you know, in addition to having the accept or reject question, you oftentimes have the question of finding a parse tree for that particular string. So if you were given this string, and you might be asked to to determine whether it's in L of G by exhibiting an actual parse tree that can generate it. And that's called the parsing problem. And that problem often comes up, well, it certainly comes up in natural language processing, but it also comes up in compilers and other things that come up in computer science. So the problem of going from a string to a parse tree, the parsing problem is a very realistic and real problem, not just in context-free grammars, but in other grammars as well. But we're seeing it only here in context-free. Okay, so context-free, the essential ingredient to being a context-free grammar, and in fact, really the only grammars I've shown you are context-free, is that you only have a single variable on the left side. So you're going from a single variable to some string here, where this string is made up of either terminal symbols or variables or some combination. And there are grammars that generalize context-free grammars that are called context-sensitive grammars, where you would have something on, you'd have more than a single variable on the left side, and therefore whether you could use it depends on the context around that variable. But we're not, that's what I call context-sensitive. Here we're talking about context-free. There is no context around this variable. It's just the variable itself. Okay. Now, I want to state a result we're not going to prove. It is actually, I think, partly proven in the book, maybe all of it. Page 106, the following theorem: a context-free grammar well, this is actually, first of all, a definition. A context-free grammar is in Chomsky. I don't think there's a P in there. No, yeah, there must be. Anyway, Chomsky. Anybody know how you spell Chomsky? Famous linguist. Famous. No P? Thank you. Chomsky, yeah. Normal form. But we just say CNF. It's in CNF if every production is of the form either one variable going to two variables or a variable going to a terminal symbol. So a single variable, of course, because it's context-free, going to two variables on the right side, or just a single terminal. And the theorem is that every context-free language can be generated by a context-free grammar in Chomsky normal form. So this one over here is not in Chomsky normal form, but the theorem says there is a context-free grammar that's in Chomsky normal form that would generate the same language that that one does. And so you can actually, if you want to take this as your sort of standard definition of what it means to be context-free, this theorem says that that's acceptable, and it kind of simplifies the view of what a context-free language is, generated by such a simple grammars of just this simple form. Okay, but we're not going to prove that. Instead, in fact, we're not going to prove anything in my treatment of context-free languages. I'm just sort of introducing you to the main results and the notation and the terminology, And you will have homework exercises, for example, using a grammar or finding a grammar or a parse tree and so on. So those direct kinds of skills, or exercises will make these definitions more concrete. But the theorems in context-free tend to be more complicated and more difficult to prove than for the regular languages. And so we're not going to take the time to actually prove these things. But I want to describe now a machine. Machines that can recognize context-free languages. And these set of machines are called PushDown Automata, or PDAs. Okay? So a PDA is actually a generalization of an NFA. So PDA generalizes a non-deterministic finite state automaton, which we're very familiar with. And in particular, what it has that's extra, well, it has to have something extra, right? Because we already know that the NFAs cannot accept, for example, the language 0 to the 1, 0 to the n, 1 to the n, right? 0 to the n, 1 to the n is not regular. And, well, here we saw a language that's very similar, and you should be able to use the pumping lemma, for example, to prove that this is not regular. Because what is this? This just looks like the language that we already showed was not regular, except that it has this extra hash mark in between. And we will see in a minute that the pushdown automaton a pushdown automaton can recognize the language 0 to the n, 1 to the n. Okay, so because these pushdown automaton can recognize a language that we know is not regular, then we know that pushdown automaton has to have something, some kind of gizmo or doohickey or whatever you want to call it, that isn't part of a normal NFA. Right? So what is it? A PDA, it generalizes an NFA, so it's pretty much like an NFA, but a PDA has a stack. It can write onto a memory device. A memory device is a stack. It can only push. Whenever it writes, it puts on something on top of the stack, and whenever it reads from the stack, it always reads from the top of the stack. So I'm sure everybody here is familiar with what a stack is. You've all taken, it comes up in programming. So it's got some extra memory, unlike an NFA. An NFA remembers, how does an NFA remember anything? Yeah, it remembers based on what state it's in. And you, as a designer of an NFA, have to encode whatever needs to be remembered in the particular states that you use. So, and sometimes it's not possible to remember what is necessary in order to recognize the language. Again, 0 to the n, 1 to the n. You couldn't design an NFA or a DFA to recognize that language because you really had no way of remembering n. N was arbitrary in length, and yet the finite state machine, any finite state machine has a particular finite number of states. So you can always make an n which is bigger than the number of states. And so there's no way of encoding in your PDAs or NFAs what the n was, so you can't match the zeros and the number of zeros and number of ones. That's the essence of why a language like this is not a regular language. But now we have a memory. It's very constrained. It's not just like a regular computer memory, random access, et cetera, et cetera. In this course, we are getting to more and more powerful machines, by adding more and more abilities, and in each stage we'll want to prove properties or see properties about their abilities. What can they compute? And ultimately we'll get up to Turing machines which are believed to be equivalent to any kind of computer that actually exists, and will prove that there are certain things that Turing machines can't do, which are certain languages that Turing machines can't recognize. And that will imply that there are certain problems that computers can't solve. Okay? But we're doing that by looking at fairly constrained machines and then allowing them to be more and more powerful. So right now what we have are these PDAs, and it looks like this. Well, the way we like to draw it, this is like the NFA part, or the state diagram. The kind of things we've been drawing so far. And now, just in order to prepare for more general machines, the way we want to think of this is there's a kind of a read head here, and it reads a input tape. And this is where the input string is written. Okay? And the read head starts at the left end. So this is the input, and here we have the NFA, which has rules in it, which says if I'm in a particular state and I see a particular character, I consume that character and I change state or stay in the same state. Okay, so far, this is just a cartoon picture of a normal NFA. There's nothing new in here yet. But a PDA also has this other thing, which is a stack. I don't know why I wrote it like that, but... Okay, and here is a read-write head. So this head can read the top of the stack, and when it reads the top of the stack, it pops that symbol off of it, and it can write to the top of the stack. So actually, if you don't want to change the stack, you can think of that as reading, and then reading a particular symbol, popping that symbol, and then pushing it back, and it stays the same. We'll also see when we give the formal definition of this that it can read epsilon off the top of the stack, which really means it doesn't read anything off the top of the stack, which means it doesn't touch the stack, it just ignores it. Okay? So in that way, it leaves the stack alone as well. So can you sort of see in general what this machine does? And it's got more power. It should feel like it has more power than a normal NFA, because it now has the ability to write something, to write information. And the size of the stack, by the way, is unbounded. Okay, so this is unbounded. It doesn't mean it's infinite. It just means there's no a priori bound. We're not saying that this stack can only be 10 deep or 20 deep. There's no bound initially. There's no bound on how deep it can go. So if you're looking at longer and longer and longer input strings, and you notice I didn't put an end here. There's no bound on the size of the input string either in general. There are some languages that only have finite strings in them. But most languages have an infinite number of strings, and it means they've got to get longer and longer because the alphabet is finite size. So this is unbounded, and we allow the stack to be of unbounded size too. Okay. The word unbounded, by the way, is different than the word infinite. Infinite, whatever that means, and I've always been very uncomfortable with the concept of infinity. But infinity goes on forever. It does go on forever. Unbounded just means there's no a priori bound on how far it goes. But on any particular, well, anyway, that's that. Okay, now let me tell you a lot more about the rules of how a PDA operates. So a PDA has components, and these are very similar kind of concepts to what we've been doing. It has a set of states, Q, okay. It has an input alphabet. Okay. That means that what's written here is something from sigma star. Okay, so the input, the alphabet of the input string is sigma, but it also has a stack alphabet. So the set of symbols that it can write into the stack comes from a different alphabet. It might be the same. Gamma might include sigma, but in general formulation, we allow this to be something that's different. It's just a particular alphabet. Okay, and then it has transition rules. Okay, delta. Now, to decide how the machine is going to move, of course we pay attention to what state it's in. So the machine, we have this NFA part, so the machine is in some state at any given moment. And what are the components that it should pay attention to when it decides what it's going to do next? That's a question.
The stack and the input alphabet?
Yeah, definitely you want to see what's over here on the input, just as we did in an NFA or a DFA. Okay? So this transition rule is going to be a function from the states and the input. So this says what's on the input. And this is also going to be augmented with what? What's a good thing to augment it with? When an NFA, when you moved from one state to another, you either consumed a character in the input or you had the possibility of an epsilon. You had the possibility of not consuming another character. And the way we wrote that, if you remember, is that you have the alphabet together with the epsilon. So again, in here, we have the possibility of reading a character in the input or not. And that's the epsilon there. But you had mentioned that we should also look at the stack. Okay? So this says, what's in the top of the stack? So in deciding what we're going to do, or what the machine will do at every step, it pays attention to what state it's in, pays attention to the input tape, or decides not to look at the input tape. What's on top of the stack, okay, or decides not to look at the stack. So this is gamma, it's an alphabet, and it's augmented with epsilon as well, which means it's reading nothing off the top of the stack, or it's reading the empty string off the top of the stack. Okay? So, but in the formalization here, we have the machine has the ability to look at the stack. All right? And well, yeah, I guess I want to put parentheses. So this is what the machine pays attention to at every step. The state it's in, it pays attention to the tape or decides not to. It pays attention to the top of the stack or decides not to. And then, what does it do? Okay? Well, as in any DFA or NFA, it decides to move to decides what state to be in next. It could remain in the same state, that's a self loop, or it moves to some new state. Okay? So this has to be Q, a set of states. Yeah?
But it's not like Q across the stack also?
Well, I'm not finished yet. Yeah, right. You're absolutely right. There's more to this. Yeah. And cross, what did you say?
Gamma.
Yeah, right. So this is what it writes. Okay? So this is the state it's going to move to, and this is what it pushes onto the stack. But it also has the ability to push nothing onto the stack. So this is, okay, gamma with an epsilon down there. So it decides what it wants to, what state to go into, and what to write on the stack, what single symbol or no symbols on the stack. Now, this would be more like a deterministic machine because it's definitely only doing one thing. Okay? One particular state, one particular act of writing on the stack. But I said that this is a generalization of an NFA. Okay? So what did we have in our description of the transition rules in an NFA? Yes. This was a set. This was a set of actions. In the case of purely of an NFA, it was the set of states that we could move into. And so this P represents the power set, all possible combinations from here. Okay? So some subset, this goes to some subset of states together with write actions. Okay, that is WRITE actions. Okay, because later in the lecture we'll be talking about RIGHT actions. Okay, so you want to distinguish those. Okay, we'll have an example. This is clearly, I think this power set here is the most confusing part of this. But again, if you were comfortable with this notation in NFAs, then you should understand it now for these guys. But we'll definitely do an example, and that'll hopefully solidify it. So this was 4. Now we have a 5 and 6. I'll put those here. What else haven't we specified yet that we typically specify in a machine? Yeah.
Just start.
Yeah, start and accept states. So again, there'll be one start state. That's the start state. I think the book is very, very inconsistent. Sometimes they use Q0 for the default notation for a start state, and sometimes it's Q0. It doesn't really matter as long as you specify what the state is, but just in terms of their general notation, it seems to vary. And then we need the accept states, or the final states, and that's a subset of Q. Okay, so this is the formal specification of what a PDA does, and this in here is the heart of it, of how the PDA actually makes progress. So later we'll write down a formal definition of what a computation is, but it's probably best to do an example at this point. Go back over here. Okay, so I want a machine or PDA that recognizes zero to the n, 1n, n greater than or equal to 0. Okay? So this is our old familiar language, which we know is not regular. But now let's specify a PDA that can actually recognize this. Actually, before I do that, anybody have an idea?
Can a PDA pop from the stack?
A PDA can pop from the stack. It pops from the top of the stack, and that's when it. Well, was what I said. I guess I didn't write it down. Is that whenever it reads the top of the stack, it actually pops it. Okay, so the read and the pop are the same thing. any sort of intuitive idea. Yeah.
What if we push the zeros onto the stack as we read them, and then when we read the first one, we'll move into a new state, and we'll stay in that state as long as we read a 1 from the input and a 0 from the stack. And then if we read a 1 from the input and we don't read anything from the stack, then it will leave that state, which was an accept state.
Yeah, I can see you're right. Your intuition is right, and there's a technicality at the end that I guess I didn't tell you about, which is that the PDA has the ability to know if the stack is empty.
Oh, okay.
Yeah.
I thought that another way would be to I thought it was 100%, but I wasn't all the way to people say it. You always, whenever you get something, you comp from the stack and then you compare them. I don't know how we do this, so we haven't seen an example.
Okay.
But,
Yeah.
If they're different, then you're good. You've got the same number, so happy. If they're the same, then you push that back on twice.
I'm going to go with the first one. It just sounds too complicated, and I'm not sure we can get back to the right. A PDA, every time it reads a symbol, a character in the input tape, that symbol is consumed. So it doesn't have the ability to go back to anywhere it had previously been in terms of the input tape.
So you can't generate them, put them onto the stack.
Well, what was suggested over here was the following kind of thing. I'll just do it with a little example. Let's say we have 0, 0, 0, 1, 1, 1. So the general high-level intuitive idea was that the PDA is going to read characters, which when it reads it, it consumes it, so that character is gone. But as it reads it, it's going to push the same symbol into the stack. Okay? The identical symbol into the stack, as long as it's still reading zeros. So we're going to have to cook up an NFA that can do that. It's just reading characters, and by its state, it knows whether it's still reading zeros or not. If it's reading zeros, it continues to push them in the stack. Okay? And then if it hits a 1, it goes into another state which says, now I'm reading 1s, and every time it reads a 1, it pops the stack. Okay? And it pops every time it reads a 1, pops when it reads a 1, and at the end of the, when it gets to the end of the input, again, in a normal DFA, if you're in accept state and you have consumed the input, then you accept. And here, you'll be in accept state if the stack is empty. So if the stack is empty at the time that you are at the end, then you accept. Now, what would happen if you had something like that? Okay, you actually let me just make it a little bit more like that. So you would stack a 0, and then you would see a 1, and you'd pop, and that would be fine. You pop the 0. Then you'd see another 1, okay, and the stack is empty, but you're not at the end of the input, and so you would be in a state which is not. You couldn't accept at that point. Anyway, let me write up the actual machine, then we'll see how it fails, how it rejects, rather than trying to hand wave that one. Okay, but the idea basically was right, that you can use that stack to remember the zeros, and then when you get into the 1s, then you can pop the stack and therefore compare the number of 1s. Every time you see a 1, you pop the stack, and you therefore, in the end, you're comparing the number of 1s and zeros. You're not ever remembering the number n. Okay, this is the language 0 to the n, 1 to the n. But you are figuring out whether the number of zeros and the number of 1s is the same, because you're pushing all the zeros onto the stack, and then you're popping whenever you see a 1. And in the end, you're deciding whether you're in whether the stack is empty. Okay. Okay, I have to back up on one little formalism here. This whole issue of how do you detect whether the stack is empty? The way the book wants to do it is, so I just said a minute ago that the PDA has the ability to know if the stack is empty. And we could allow that. That doesn't get us into any trouble. But actually the book doesn't. What the book says is at the beginning of the computation, the PDA is going to write a symbol down here which is not part of the input alphabet. Its first symbol it pushes onto the stack is going to be like a $, which is not part, it's not from the alphabet, it's not from the terminal alphabet. And so whenever it hits a $, that's equivalent, whenever it reads a $, it's equivalent to knowing that the stack is empty. Okay, so just a technicality there. All right, also, just in terms of shorthand notation, so we're gonna write up a diagram here, and what we're going to write. So this is this is state Q1, which is not only a start and a accept state, and then we're going to have something written on there, which in this case is epsilon goes to $, goes to Q2. But I want to explain this kind of notation in more generality. So this is actually the first, what's written on that first edge. But in general, what does that mean? If you go from one state to another, okay, then A, B, C. A is what's on the input tape. B is what's on the stack. And C is what you write onto the stack. So in general, we're going to write that onto an edge, and Qi, Qj. So this specifies a transition. According to our transition rules, it says if we're in state Qi, and you see an A on the input tape, and you see a B on the stack, then you move to Qj, and you write a C on the stack. Remember that when you read a B, you're also popping it. So the top of the stack changes from a B to a C. Okay? And you've consumed the A, which is part of the input. Okay, does everybody see that that notation, that shorthand notation, is consistent with this, with what we wrote here? Here it says in order to do a transition, you need to know what state you're in, you need to know what you're reading on the tape, on the input, and you need to know what you're reading from the stack, what you're popping from the stack. And then you go to some set of states, some subset of this Cartesian product, which is a state cross what you're going to write onto the stack. So here, this is just a single transition rule. That notation means that we could have had other ones as well in here. It could have been XY goes to Z. All right, that if you see an X and on the tape and a Y on the stack, then you'll replace the Y with the Z. Okay, so you can have, because that's a power set over there, you can have many, and no, that's not. I'm sorry, that's not the reason. You can have many. You can have here A, B goes to Z. This is what's illustrating the power set idea and the non-determinism. So you're in state Qi, and you see an A on the tape, a B on the stack, and you can decide to replace the B with a Z and go into QK. This is what the power set allows you to do. You could also have this, that's fine, but that's not part of the, that isn't because of the power set, that's just, we've always been able to do things like that. Okay, so over here, what is this really saying? Yeah?
So do you mean that in that non-deterministic thing you have there that you're going to end up with 2 stacks?
Sorry, say that again?
Do you mean that you're going to have 2 stacks there?
2 stacks, why 2 stacks?
Because you're saying that B can become C or B can become Z.
No, it depends on oh, here, you're talking about this one.
Yes.
No, well, it depends. Remember, in non-deterministic computation, when you have choices, you spawn off the machine. You make a new machine. So one machine is going that way, it's making that action, and one machine is going that way. So in each one of these machines, each one only has 1 stack. Okay?
So there's 2 stacks.
Well, in each machine.
So there's 2 machines each with its own stack.
Yeah, 2 machines each have their own stack. Yes, right. So non-deterministic computation, whenever there's a choice, you're actually spawning off a new copy of that machine, but now it's doing different things, and then they can spawn and so on. Or you could think of it as there are all the different possible ways that you could do it. You can traverse through this PDA or in general NFA, and you're either thinking of doing them in parallel, or you're thinking about what is the set of all possible computations that could be specified by this machine. But at any rate, any one machine at any given time, any one machine only has 1 stack. Did that answer your question? Yeah. Yeah.
Okay, so you have A, B goes to C. After that, will B still be on the stack or will it be gone?
B is gone. Yeah. When you read from a stack, when you read the symbol on the top of the stack, you're popping it at the same time. So
You're not implicitly rewriting B.
it's what?
You're not implicitly rewriting B.
That's right. Yeah. Right. When you read from the top of the stack, that symbol is actually popped. Now, if you want to put it back, you can do that. You could have A, B goes to B. That means you read B and you put it back. Okay? So that's certainly legal too.
Can you write multiple characters to the stack in one transition? Can you have A, B,
No, that's not a formalism that's allowed, but you can implement that if you really wanted to do that. So if you got to a particular state and based on what you read, you decided you want to put multiple things in the stack, then what you would do, you have, let's say, QI goes AB, and let's say we want to actually put CD on the stack at that point. Take the B off and write CD. Okay? So then we could go into a state. Okay, sorry, this goes A, B to C. We go into a state, and what should we do in this state? Yeah, you can do an epsilon goes to D. Okay? And as long as that's the only option at that point, that does exactly what you had suggested. This says, don't even look at the tape, at the input. Don't even look at the stack, but push D on it. Okay? So you can in effect do what you wanted, but the notation, unless we decide to change it just for simplicity, the formalism of the notation doesn't allow you to put more than a single character on the stack at any individual step. But you can program it if you want to do it that way. Okay, so what this is doing is initially, this is the start state. So initially it's not looking at the input, it's not looking at the stack, but it's writing a $ onto the stack. So I mentioned this earlier, this is how the book, or how this notation, this formalization, is going to be able to detect the bottom of the stack, that is when the stack is really empty. Because if it ever reads a $, then it knows that it's at the end. So whether you allow a PDA to detect that the stack is empty, or whether you always do it this way by putting this as at the very beginning of your PDA, it's the same thing. All right, so that was the first step, or first state. 0 epsilon goes to 0. Okay? So what is this doing? Let me take this away. This is saying if you see a 0 on the input tape, you're not even going to read what's on the stack, but you're going to push a 0. Okay? So this is doing what was suggested over there, that as the machine is reading zeros, consecutive zeros, it's pushing those onto the stack. That's what this is. Push zeros onto the stack. Okay? Then what happens is if we see a 1 in the input and we have a 0, if we see a 1 in the input, so here we're just continuing to go around, as long as we're seeing zeros, we're stacking them. Then if we finally see a 1, and there happens to be a 0 on the top of the stack, that's doing the correspondence between a 1 and a 0, and we write onto the stack an epsilon. So one of the zeros has been popped off the top of the stack, and we don't write anything on there. Okay? Q3. What should we do in Q3? So this was the change here. We were seeing zeros. Now we're seeing ones. We're into the region of the string where we expect we're going to see ones. What should we do here? And what?
The same thing as from Q2 to Q3.
I hear a voice. Wave at me. Who's saying that? Oh, yeah. Okay.
The same thing as you do from Q2 to Q3. Keep popping zeros as long as they're on the stack.
Yeah, right. We're going to do the same 1, 0 goes to epsilon. So again, what this is doing is, as long as you're seeing a 1 in the input, and as long as there's a 1 on the top of the stack, you're popping the stack and just popping the stack. You're not writing anything. Okay? So that keeps going for a while. And then Q4. Now remember, this is like an NFA. Okay, so it can do this as long as this is still working, but it can also decide, like an NFA, to go over here because this is an epsilon on the input. Okay, so it can decide, well, I'll do nothing. I won't look at the input, but I'll check that the top of the stack is the $sign. That is, this is checking whether or not the stack is empty. And then I write nothing onto the stack. Okay? And I accept. I'm in the accept state. Sorry. I'm in the accept state. Now, is this really an accepting computation? Well, it's just like a DFA or an NFA. If you're in an accept state, you end up accepting if you've consumed the entire input. You could be in an accept state and not accept, and you won't accept, in fact, you'll reject, if the input string is not fully consumed. So if we go over here too early and there's still symbols left in the input, the stack might be empty, okay, but the sequence, the input sequence isn't fully consumed. And what would that mean? If the stack is empty, but the input sequence isn't fully consumed, then we definitely don't have the same number of zeros followed by the same number of ones. We have some number of zeros followed by a 1, an equal number of ones to the zeros we've seen, but there's something left over. It could be another 1, it could be another 0, but whatever it is, it demonstrates that what we have is not some number of zeros followed by an equal number of ones. And so that's definitely the right thing to do, is to reject at that point. Okay? So, on the other hand, there is a computation. If what you have is the same number of zeros as ones, there is a computation in here which does end up accepting. okay? Because that computation is you stack 3 times, okay? And all of this is deterministic. Over here, you pop 3 times while you're reading the ones, and then at that point you move over to here, you're reading the bottom of the stack. It's that $sign that you put there to recognize that you're at the bottom of the stack. The input is fully consumed, you're in an accept state, so you accept. So this non-deterministic machine, whenever it has input that's actually of the 0 to n, 1 to n form, this machine has a computation that will end up accepting that string. As in most NFAs, it also has a computation with that string that doesn't accept it. But in an NFA, in a non-deterministic computation, all that's required is that at least one of the computations on that input accepts it. And that's what I'm arguing, is that there would be a computation that accepts a string of this form. Okay. Now we have to try to convince ourselves that if the string was not of that form, then there's no computation in here that will end up accepting that string. Okay? So if the string is not of that form, then what form is it? It's got some number of zeros initially, which might even be 0 of the zeros. So what happens if you have no zeros at all? Okay, well, either you also have no ones, in which case it's the same number of zeros and ones. So is n greater than or equal to 0. Equal to 0 is permitted. So it does the right thing, it accepts. Okay, but suppose it had no zeros, but the first character is a 1. Okay, well, here there is no, oh, sorry, it will go this way, absolutely, because this is just an epsilon, epsilon. It goes here, there's a 1, so it goes there. Oh, yes, right, sorry. Yeah, here it will not go there because it checks to see a 0 in the stack, and so it can't follow that transition rule. Okay, there's no transition rule that it can follow, and just as in an NFA, when you're in a state and there's no transition that's allowable in that situation, that computation dies. Okay. Again, I'm saying that computation dies as opposed to saying that machine dies, because in NFAs you're spawning off replicate machines. Now, in this case, we haven't spawned anything at this point, and so that computation dies, which means all the computations die, which means that's a reject. No computation ended up as an accept, so that's a reject. Okay, so that was just a special case of a string that began with a 1, and we're seeing it's doing the right thing. So then we want to say, well, okay, let's suppose it starts with a 0. It'll have some number of zeros, let's say k, all right? And then either it has some number of 1s, let's say L less than k, then it's followed by a 0 again, or it's going to have some number of 1s, L greater than k, or it's going to have L equal to k, but then we're going to, so I actually probably should have this, well, L equal to k, but then there's another 0, okay? And so these are all the cases, this is a way of describing all the possible sequences, in addition to the one that I already talked about, all the sequences that are not of this form. And then you should convince yourself that in each of these cases, none of the computations that this machine allows will end up as an accept. They'll all end up stuck somewhere where there's no next transition, or they'll be here, but the input string has not been fully consumed. Okay, so either way, that computation will end up being a reject computation, and there's no accept computation. Okay, so I'm going to leave it up to you to fully validate, convince yourself that this is an actual correct PDA for this language. And So this PDA is clearly more powerful than an NFA because we know there's no NFA that can recognize this language. So stacks actually help. Okay, next example.
I have a question.
Yeah.
So usually the notation where an edge had a comma in it meant that that edge you could take different inputs to get, for that edge.
Yeah.
Can we still accept multiple inputs on an edge, or is that gone in PDAs?
Oh, right. You're talking about whether we have something equivalent to a GNFA. Oh, no, sorry, what you were...
I mean, can we say this edge accepts 0 and 1 as input? Because here you don't do that at all.
Well, we can have multiple ways of moving from here to here. That's just a representation of multiple rules, transition rules.
What
Okay.
I mean is, if you had an if you're going to the same state, I guess, and you're going to do the same thing with the stack, with all possible inputs, and you're using binary, would you have to create two edges, or is there a notation where you just say 0, 1, comma, and then the stack stuff, or would you have to have two edges for that?
Oh, okay, so you're saying we could have a rule which is A, B goes to C, or we could have A, B goes to D. That's certainly permitted. This is a non-deterministic computation, so you decide either to do that one or that one.
I mean, could we say like
BB goes to C, is what he's asking.
B goes to C. Sure. Is that what you're asking?
more like A, comma, B, comma, like C goes to D or something like that? So I don't mean to reuse variables.
Unless I can understand the question, I'll just say no, but let me see if somebody else can clarify it.
I think he means like A union B union C, comma, C goes to C.
Well, okay.
A bunch of the same.
Yeah, I mean, that's the shorthand, which is, so the formal answer is no. You can only do what we've defined. But just as the earlier question asked, can you actually implement something like that where you have multiple choices for what you're reading here? Yes, because we have the ability to have multiple rules here.
It was a notation question. I know that you can implement it.
Okay. It was a notation question?
Yes.
Yeah, okay. Notationally, you can invent all kinds of shorthands that are very helpful to you. But in the end, all of those have got to be translated back to just the formalization that we've put here. Okay.
So under that formalization, he's saying, do you have to write an arrow for each possible, like the A, comma, B goes to the beginning, or do you just keep stacking them on the same paragraph, or do you put each one in parentheses with a comma between them, or something like that?
Well, no. If you have multiple possible transitions or multiple rules here, okay, which have the same state and you're going to the same state here and have, you're saying...
Where only the input alphabet differs.
Yeah, where only this differs. According to the notation we've done so far, you would have to write each one of those as a separate arrow. And I think what you're asking is, well, that's awfully tedious. Can't I just do something that clearly indicates what I mean? And in general, the answer is yes. I mean, we want to be able to do that, but the formal answer is no. The formal answer is this is how we're defining what a PDA can do, and writing it up right now. If you're doing your homework and you clearly explain what you mean by some other notation and it isn't too bizarre, you could probably do that. I think Sean could understand that. But in terms of the formality of what a PDA is, this is the way it's defined.
You wouldn't need, for this case, you would need another arrow going underneath B, comma, B goes to C. Or do you
Another...
just say that?
Sorry, say that again?
Because you have for QI to QJ, you have both those two possibilities.
Yeah.
Do you just put it like one above one?
Yeah, right. It would just be, here are the various rules that are that go there.
What if you had 3? Would you want another arrow for that, or
I would just list them all.
Okay.
Yeah. I mean, okay, so, all right. So I see your bigger point is that the book hasn't made it completely clear. Should you put another arrow there? This is now really just a matter of your own convenience, I guess. The more arrows you put, the more cluttered it gets, but, yeah. Okay, so let me give you another example I think I want to do. Of a PDA. So this language is WW reverse. W is contained in 0, 1 star. Okay, so this is going to be some binary string followed by the reverse of it. So for example, 0, 1, 1, 0. There's a sort of a normal, there's a word in English for such kinds of strings. What is that? Palindrome, yeah. Okay. So a palindrome is a string that reads the same forwards and backwards. And there's a book that just came out that's got incredibly long palindromes, stories that are like 3 or 4 pages long, and it's a sensible story. It actually reads, it makes some sense, and then it's the same backwards. This guy was incredibly creative in coming up with long palindromes. Anyway, this is it reads the same forward and backward. And how many people have taken molecular biology here? Studied some biology? Okay, a few. Okay. Well, anyway, I won't digress. I was going to talk about palindromes and molecular biology and confusion between cultures and the difference between biologists and mathematicians. And that could go on for a long time, so I won't do that. But you can come and ask me later. It's an interesting story. Okay, so we want a PDA that recognizes palindromes. So first thing we're going to do, what's the first thing? Anybody have any idea what the first thing is we're going to do?
Epsilon.
Yeah, we're going to be using a stack, and again, we're going to probably want to know if the stack is empty, because this certainly has got to be the same length as that. It's the reverse, but the length has got to be the same. And so we're probably going to put something on there that, put the $sign in there so that we can recognize that the stack is empty. And then we're going to have a state here where essentially what we have in mind is we're going to read the first part. Now, we don't know what the first part is and what the second part is. So this would be very difficult to do with some kind of deterministic machine. But we've got the power of non-determinism. We can always guess. Another way that people talk a lot about the use of non-determinism is that the machine guesses what the right next thing to do, or when to move from looking at the W to the W reverse and so on. But in fact, when we say guess, what we really mean is you do both in parallel. You do all the possibilities in parallel by spawning off new machines. But so here, we're accumulating W. So in that, or so this is the part of the machine that's going to accumulate or push W onto the stack. So all it's really doing is taking whatever it reads on the input and making a copy, pushing that onto the stack. It's not popping anything because it's reading epsilon. You can think of it as it's popping epsilon, okay? But so this is now the stack is growing in size, and here it's growing in size also, but by a 1 if that's what is being read in the input. And then it's guessing that the right thing to do is to start looking at, it's guessing that the rest of the string is going to be W reverse. Okay? Now, how does it know that it's finished with W? It doesn't. But that's the power of non-determinism, is that one of the computations will decide, yeah, now it's the time to go from W to W reverse, and another one of the computations will stay here, accumulating more characters, guessing that, no, the W part of the string is actually longer, and we're going to make all possible guesses. And one of them will be right. So one of the computations, if the input string really is W reverse, one of those guesses will be correct. And that's the power of non-determinism versus determinism. Okay, so here we're just we're looking at the input, and we're looking at what's at the top of the stack. Okay, and because we're reading the top of the stack, we're also popping it. That symbol is coming off the stack, and then we're not writing anything more onto the stack. All right. Now it takes a moment to think about this. Why should these things be the same? Why is that? After all, we wanted a reverse. How is this implementing reverse? Yeah.
Because the stack is first in, last out.
Yeah, because of the nature of the stack. The stack is first in, last out. Okay, so that again, if the computation guess is at the right point, it goes over here. What's on the stack at this moment is 0, 1. It is the reverse of this. What's on the stack, if you read from the top to the bottom, is the reverse of what you just read. And so then when you go through the rest of the string, in order to find out whether this is equal to the reverse, you do want to check whether this is equal to that and this is equal to that. And that's what this is doing. It's popping the stack. It's looking at one character on the tape, popping the stack, reading the stack, and if these two are equal, then it's going to epsilon. What happens if they're, well, I haven't finished this thing out here, so epsilon, $, epsilon, Q4. Okay, so now you see what's everything out of Q3. So what happens if you read a symbol on the tape, let's say a 0, and what's in the top of the stack is a 1?
That computation dies off.
Yes.
Still doing the top ones from. There's probably still some going on. Or there might be.
Well, yeah.
Maybe one of those ones.
Right. But that computation definitely dies off because there is no transition rule here which says 0, 1. Okay, 0, 1. That's not in there. And so the computation that's here, reading a 0 and having a 1 on the stack, has nowhere to go, so that computation dies. Right? Now, as was pointed out, maybe some other computation succeeds. All right? In fact, if we take the computation that stacked the first 0 and then decided to go over here, then that would be exactly that situation. But yet there's some other computation which reads 2 symbols here first and then goes down here. And the computation that reads 3 symbols first before it goes down, that will also, that computation will also fail or die. Okay? How would that happen? It reads the 0, it reads the 1, it reads the 0, it stacks that, it comes down here, and now it has a 0, it's reading a 0 and looking at a 1 on the stack, and it dies. Okay. The last thing here is that it moves over to the accept state if it's seeing a $sign on the stack. So if it's at the bottom of the stack and it reads nothing and it writes nothing, and it's over here in the accept state, and the computation accepts, but only if the input is actually fully consumed. Okay, so just like a DFA or NFA, this machine has the ability to know whether the string is fully consumed. Yeah.
Does the PDA allow you to accept if the stack still has characters
is the PDA allowed to accept if the stack, yeah, the rules of a PDA allow you to accept, but this particular one won't because of this rule. And it depends on what language you're trying to implement. There certainly could be languages where you would accept even though the stack is not empty. So it depends on the particular language and the particular PDA. It's allowed under the rules. It's not used in this particular PDA or in the previous PDA that we looked at. And sort of the obvious power of PDAs over NFAs is, well, in languages like this, which are sort of the immediate ones you think about when you want to go beyond regular languages, then you would only accept when the stack is empty. But anyway, to answer your question, the answer is yes. If you design your PDA appropriately, you can do that. Okay, so now we know about these more powerful machines, and you'll have some exercises where you design PDAs to recognize particular languages. And again, it should be clear I hope you fully understand what it means for the PDA to accept or to recognize a particular language. And remember that it's a non-deterministic machine. And so it can make many guesses, many choices. It will make them all. And if one of those computations accepts, then that string is accepted. Okay, let me state now the major theorem, which we're not going to prove, but the major theorem about context-free languages. So we had a definition of context-free languages based on the grammars. And now we've been talking about these PDAs, and we've looked at some languages. What do the two parts of this lecture have to do with each other? So a definition of context-free languages and context-free grammars, and then we've been playing with these PDAs. Why did I put these both in the same lecture? Because, say that again?
You can recognize the context-free languages and PDAs.
Because a PDA, every context-free language is recognizable by some PDA. Is that what you said, or meant to say?
But that's probably.
That's what you meant to say, yeah. And what about?
I was thinking the same thing. Any CFL can be recognized by some PDA.
Okay. Anything else?
Probably reverse.
The reverse, yeah. Okay. So the major theorem. A language is a context-free language if and only if it is accepted by some PDA. Okay? So just as we were able to characterize regular languages as those languages which were recognized by DFAs, they're exactly equivalent to the set of all languages that were recognizable by DFAs, and those were actually equivalent to the set of all languages that were recognizable by NFAs. Here we have this set of languages, the context-free languages, are exactly equivalent to the languages that are recognized by some PDA. So we've defined context-free languages by the languages that are generatable by context-free grammars. And we have a machine here a PDA that can recognize languages. And the set of languages that are generatable by context-free grammars and the set of languages that are recognizable by PDAs, those are exactly the same set of languages. Okay? So this is a much more mechanistic, PDA is a much more mechanistic way of thinking about context-free languages, and the grammars are much more, well, it's a mechanistic way of generating strings in a language. Okay. All right, so this is what I was going to do in the first half hour of today's lecture, talking about PDAs. And I should mention the book also, this chapter has a lot more than what I'm talking about in terms of PDAs and context-free languages. The book shows a pumping lemma for context-free languages, which is much more complicated than the pumping lemma, and its proof, much more complicated than the pumping lemma for regular languages. But with that pumping lemma, it allows you to prove that certain languages are not context-free. So they're languages which are not even context-free. And it can be, they can be proven, okay? And you should take a look, just skim that and see what some of the languages are that they prove are not context-free. We're not going to do that. It's too complex and diverts from what we really want to do next. Okay, so there's a hierarchy of more and more powerful machines. So we DFAs equals NFAs, and we have PDAs, and there are some other ones, but the outermost ring, the most powerful machines, are called Turing machines. So the next chapter, and what we're going to talk about, what I was hoping it was going to be the main topic of today, but we'll make it the main topic of Thursday, is jumping all the way to the most powerful machines, which are Turing machines. And a Turing machine is going to be much closer to a real computer, and we're going to have things like programs and algorithms, and it'll be much more like programming, except that, how many people here have programmed in real rock-bottom assembly language? Okay, you know how grotesque, tedious that is. Okay, programming a Turing machine is like 1,000 times worse. Okay, so a Turing machine is as stripped down model of a computer as you can imagine, and we'll write some little programs. We don't actually implement them on anything. We'll write some little programs so you get a sense of it. And the Church Turing, there's some other names to it, thesis, which has never been violated, is that anything you can do in any of your existing computers on existing languages that you all use, like ALGOL. No, in the days that this was written, people talked about ALGOL. Any real modern computer language, you can translate that down to a Turing machine. A Turing machine can do anything that a real computer with a real programming language can do. It's just really stripped down just to show you the bare essence of things. So we'll get to that next lecture.